Hello, welcome back. In this segment, I will show you an abstraction of Feistel network using Python. So I request you to watch the previous segment, otherwise it will be difficult to follow this particular segment. And the abstraction is really simple. I define Feistel network as follows. There's a left component, there's a right component, and a bunch of keys and a PRF. Why do I do that? Because you may recall from the previous discussion that a block is partitioned into two things, left block and a right block. And they need not be equal size. Although in my previous demo, I used a balanced Feistel network. They need not be equal size, but let's assume for simplicity, they're equal size, okay? So you have left part and the right block of your plain text. When I say plain text, it could be message, it could be image, whatever, just a bunch of bits essentially. And what we do is in each round, we call the underscore Feistel network. Okay, what is the underscore Feistel network function? The underscore Feistel network function is defined here. It takes the left block, the right block, and a particular key and a PRF. As you can see here, I call it keys. Here I put keys, and here I just say key because this is just one round of Feistel network. And we are calling the underscore Feistel for all rounds. Okay, so I am using the same PRF. Feistel network allows also you to use multiple PRFs. Okay, for each round you could use a different PRF. That's not a problem, as long as we are consistent using the same PRF during decryption. We should be fine. So this is the structure of the Feistel network in Python. Very high level abstraction. You have to plug in a PRF, of course. It could be a one-way function. Keyed function, of course, should be the PRF that you could plug in. Okay, so let me draw a picture to make all of this senseful quickly. So we have a block, right? A block is made of two parts, left part and the right part. Although I tried to show it equal length, but it need not be. So this is the left part, right? This is the right part. Okay. And then what we do, we take the right part, right? And feed it into a pseudo-random function. Let's call it PRF function F, right? It's a keyed function. So first round we'll use FK1, the key round 1, right? A keyed function first round, okay? And we feed the right as it is to the next round. So it's copied as it is, but also we send it to this pseudo-random function. This F is a pseudo-random function. This is the F, right? This is the F that I'm talking about. And we get the output and we XOR it with the left block, right? And then we continue the next round. Okay. So this is exactly what I modeled here. So we start with the Feistel network. We feed in one block, left block and right block. You can imagine two blocks put together as one block. So this is the left block, this all the bits here, and the right block is all the bits over here. Okay. The conversion from a text to a sequence of bits is outside the scope of this abstraction. You have to do it outside. But once you have the left block and right block, you need to pass a key arrays, right? This is the array of keys, because in the next round I will be using, here I am using K1, in the next round I will be using K2 and so on. So you need to pass an array of keys. Okay. And then the PRF is fixed. The PRF is this function F. We don't know what it is. From a Feistel network perspective, PRF itself is a black box. Okay. So that's the reason I modeled the abstraction like this. So once you get the output, we use the output from one round to the next round. That's what I'm doing here. You can see here, the left and right is the output I got from the Feistel network, and that becomes the input to the next round. So left and right. Okay. Now let's dive inside the underscore Feistel to understand how the underscore Feistel works. So underscore Feistel essentially does whatever the image is showing you here. It is basically taking the left side of your message, that the L block, and calls the PRF function, right? You see here the PRF function is called using the key and the right side block. Okay, this is the key stream. You get a key stream by calling the PRF, okay, using the key K1 or whatever key that we are passing from here. This is the key array. And then we take the left block and XOR it with the output we got from the pseudo-random function. So this is the XOR. The symbol is XOR in Python. It's not exponent. Okay. So this is XOR, this is XOR, this particular thing. Okay, now, as I said here, we take the right and put it to the left. We take the output of the XOR and put it to the right, and that's exactly what I'm doing. So the right is basically a copy of whatever right was passed, and the left is the XOR output, and that becomes the, as you can imagine here, the left is now assigned to the right, which is exactly what we need here, because the next round the left is same as the previous round's right, and the next round's right is same as the previous round's XOR of left and a pseudo-random function on the right. Okay, and that's all. So this is basically Feistel network abstraction. Of course, you need to plug in a good pseudo-random function that this is the parameter you need to plug in. Python allows you to pass functions as arguments. So it's much clean abstraction when I talk about Feistel network in Python. Of course, you can do the same in C as well, function pointers. And then you are essentially calling your Feistel network function underscore Feistel for each round, and take the output of the previous round and just swap it. That's essentially what's happening here. And continue the Feistel network for each round. Okay. And I kept it so abstract because you can pass any keys that you wanted. Key scheduling algorithm itself is outside the scope of Feistel network. Usually you don't deal with many keys. You have one master key K, and from there you're deriving bunch of keys K1, K2, and so on. Suppose you have 16 rounds, then you will derive 16 rounds. I'm just making up an example. That is outside the scope of Feistel network. You are supposed to derive keys securely from one key to all the key rounds. That's usually done by a key scheduling algorithm. You don't do it manually either. Okay, that's basically it. Thank you for your attention.